Hello, welcome back. Today we're looking at thermal equilibrium. So today you should be able to establish what thermal equilibrium is and think about what we call the zeroth law of thermodynamics. In thermal equilibrium, we think about the energy being conserved, and this process is called calorimetry. So you have two objects touching, two pieces of metal, two solids touching, different temperatures. They are going to eventually become in thermal equilibrium. So the heat will transfer from the hotter object to the colder object. And if there's three objects that are touching, and the first two are in thermal equilibrium, the zeroth law states that if two bodies are in thermal equilibrium with a third body, they are in thermal equilibrium with each other. So everything's in equilibrium. They're all the same temperature. There's no more heat transfer. So you can see here I've got an example, three pieces of metal, brass, iron, aluminium. They all have different temperatures. Eventually, the heat is going to transfer and all three of them are going to become the same temperature and have thermal equilibrium. Okay, so let's dive into this a bit further. Calorimetry is the science of measuring the amount of heat transferred between objects or in a chemical reaction. So it works with the principle of conservation of energy. In a closed system, the amount of energy gained by one object must be equal to the amount of energy lost by another. So the energy from, say, brass into the iron is equal. So the energy lost from the brass is gained by the iron in a closed system. So mathematically it looks like this. The thermal energy lost plus the thermal energy gained is equal to 0. So we're measuring the amount of heat transferred between objects, and we're using this equation to help us in this measurement. So I want you to reflect in your own words. What is it meant by thermal equilibrium? Okay, so hopefully you thought about what is thermal equilibrium. You're comfortable now. We're going to try and use this equation to solve a problem. So let's go back to my three pieces of metal. Let's imagine we've just got brass and iron. And let's say each cube is 1 kilogram. So we know that Q lost is equal to the negative Q gained. So the lost heat thermal energy is equal to negative the gained thermal energy. We know the masses are both 1 kilogram. Specific heat capacity is different. So brass is 380. Brass is losing energy. We're going to change this change in temperature to final minus initial temperature. 1 kilo, and we have iron. Iron is 460 heat capacity, specific heat capacity. Alrighty, so we don't know the final temperature. Let's figure out what are their final temperatures going to be. Oh, you probably need to substitute in the initials as well. So brass initial is 60, iron's initial is 50. Now we're going to rearrange, and they're going to be in thermal equilibrium, so their final temperatures are going to be equal. Alright, so let's expand the brackets. This becomes 380 TF minus 22800 equals minus 460 TF. And don't forget this bit. Negative times a negative is positive. Very common error. So don't forget to times the negative times. A negative times a negative is a positive. Write yourself a note. All right, now we're going to use some algebra, bring the TFs together. So we're the opposite of negative is positive 460 TF. And the opposite of 22800 is plus 22800 to both sides. So that brings that one over to this side and this one over to this side. So now you'll have, and now we add these two together and these two together. Divide both sides by 840. So the temperature final for both of them will be 54.5238 degrees Celsius. So you can see, if we're just looking at brass and iron, the brass has gone down to 54 and the iron has gone up to 54. Now obviously these two are both also going to be in equilibrium with aluminium. So aluminium is going to bring them up. So they're both going to be higher than 54. But that's just the beginning of the problem. So I would continue working to do aluminium as well to figure out what they would final temperature equilibrium of all three would be.